Assalamualaikum. Let's start lecture number 39 that will be related to the uh, problems for the transformation of plane stresses, in which we will see how to find the principal stresses and maximum shearing stress, and we will consider the Mohr circle as well, and we will draw Mohr circle for that as well. Okay, let's see problem starting with this 7.5, and we will see 7.9 as well. For the given state of stress, determine principal planes and principal stresses. So the stress state is given, 60 megapascal is compressive, 40 is also compressive, and we have a shear stress of 35 megapascal. Means if I draw, so if I take this is my x-axis, and let me take this is my y-axis, so I can write sigma x is minus 60 megapascal, sigma y is minus 40 megapascal, and tau xy I will take positive 35 megapascal. If this shear stress, this over here is acting downward, then I will take negative value of shear stress for this problem. Okay, now for the maximum principal, for the principal planes, we know that part A, so tan 2 theta p is equal to 2 times tau xy divided by sigma x minus sigma y. And if you put the value 2 times 35 divided by sigma x is minus 60 and plus sigma y, sorry, not plus, that will be negative, minus 40, and that will be equal to minus 3.5. So 2 theta p will be equal to minus 74.05 degree, or theta p will be minus 37.03. That will be one axis principal plane. The other plane will be plus 90, means 90 degree apart. So that will be 52.97 degree. Means if I rotate this obviously in clockwise direction, so if I rotate this, or if I find the stresses, state of stress, if I rotate this in the clockwise direction, and this will be theta is equal to 37 degree, 0.03 degree. So over there we will have principal planes. So principal stresses will be on the location, those on that location. Okay, now part B. So we have to find principal stresses. So those are the maximum and minimum normal stresses, and the shear stress at that orientation will be equal to 0. So that will be sigma x plus sigma y divided by 2, that is average stress, plus minus under root sigma x minus sigma y divided by 2 square plus tau xy square. So let's calculate. Okay, so sigma x minus 60 minus 40 divided by 2 plus minus under root minus 60 plus 40 divided by 2 whole square plus tau xy square, that is 35 square. So minus 50 plus minus, we calculate 36.4. Now sigma max will be minus 13.6 megapascal, and sigma minimum will be minus 86.4 megapascal. So that's you can calculate the maximum and minimum principal stresses, and those principal stresses will be along the principal planes. Okay. Okay, let's see this problem 7.9. That is again linked to the previous one. So again, if you look at this problem, so in this problem we have to, for given state of stress, we have to find orientation of maximum in plane shearing stress. So what is maximum in plane shearing stress? That will be, we will discuss when we discuss Mohr cycle for 3D. So over there we will discuss what is in plane and out of plane shearing stress. So currently we are only consider the maximum shearing stress. And second part B, we have to find the maximum in plane shearing stress and corresponding normal stresses. So again, let me draw, this is my x-axis, this is taking my z-axis, sorry, y-axis. So I can write sigma x is equal to minus 60 megapascal, sigma y is minus 40 megapascal, and tau xy is 35 megapascal. Now, part A, maximum, where the location for maximum shearing stress. So we know that 10 to theta s, that will be equal to minus sigma x minus sigma y divided by 2 times tau xy. So putting the value, minus 60 plus 40 divided by 2 times tau xy is 35. So when we calculate, so this will become 0.2857. So 2 theta s is 15.95 degree, and theta s will be 7.97 degree, and the other will be obviously 97.97 degree. So positive sign means if I rotate this with angle, so this will be theta s, this angle, and this will be equal to 7.97. Positive means counterclockwise direction. Okay. Now part B, we have to calculate maximum in place shearing stress. So tau max is equal to sigma x minus sigma y divided by 2 whole square divided by plus tau xy square. So putting the value, that will be minus 60 plus 40 divided by 2 whole square plus 35 square. And if we take under root, so this value will be, tau max will be 36.4 megapascal. And the corresponding shearing stress will be average stress. So sigma average, that is sigma x plus sigma y divided by 2, and minus 60 minus 40 divided by 2, so that will become 50 megapascal, but negative means compressive. Means if I draw the element, so that will be if I rotate it with 7.9 degree, so we have maximum shearing stress, tau max, and that tau max will be equal to 36.4 megapascal. And corresponding shearing stress will be compressive, and that value will be equal to sigma average 50 megapascal. and that is we are simply rotating with the angle of 7.9 degree in clockwise, counterclockwise direction. Okay, so that's how we can find the maximum shear stress and the corresponding normal stress for the problem as shown over here. Okay, now let's see this problem 7.23 that is related to the application of this chapter, transformation of stresses. And let's see the problem. The axle of an automobile is acted upon a force and coupled. So let's suppose this is an axle of an automobile where we have a 3 kilonewton force acting upward and 3 kilonewton acting downward with a distance of 1.5 meter from this, and from H it is 3.5, and this 3 kilonewton acting downward is 2 meter distance, 0.2 meter from H, and couple, and this moment is also acting, and that is 350 newton meter. Okay, knowing that if the diameter of the solid axis is 32 millimeter, means the diameter is given is 32 millimeter. So first we have to find the principal planes and the principal stresses at point H located on the top of the axle. So on this point we have to find principal stresses and principal planes, and part B we have to find the maximum shearing stress at that point. Okay, now in order to solve this problem, what we have to do first, we have to take a section over here, taking a cutting plane and passing through that section, and we will transform our force moment system to the center of this section. Means if I draw it, let's suppose we have a circular section, this is point H, and on the centroid we have to transform our force moment. So what we have one moment and torque, so that will be acting. So let me write T is equal to 315 Newton meter. Now the transverse force 3 kilonewton plus and minus, it will cancel, so there will be no transverse force acting on that section. So what else? Now we will have a bending moment, and that bending moment will be acting on this point. So let me take this axis, and what it will be? It will be the bending moment. Let me write over here equation. Bending moment will be equal to 3 kilonewton multiplied by 0.35 minus 3 kilonewton multiplied by 0.2, and that bending moment will be equal to 450 Newton meter. 450 Newton meter. And the direction, so the direction will be like this. Okay, let me put my negative over here, positive over here, clockwise and counterclockwise direction. So minus, so as this direction, at this direction it's showing in this way. Means now due to this bending moment at H, it will be top surface and it will be under compression. Means if I look at the top view of the axle, so it will be something like this, and this point H, and we are taking a small element at H, and we are interested what is the stresses over here. Now if I consider this H, and if I exaggerated it, so H, so I'm making a zoom view. So let me take, this is my x-axis, and this is my, let me take, this is my y-axis. and this is at H. Now we have a stresses, normal stress due to bending, and we have a shear stress due to torsion. Okay, now due to torsion, due to bending, but first let's calculate I and J. So if we calculate I and J, so I will be pi by 2, sorry, pi by 4 C4, and J will be pi by 2 C4. And over here C is the radius of the shaft, so that will be 32 divided by 2, 16 millimeter, or we can write 0.016 meter. Okay, now stresses due to bending moment, sigma m at H, so, and that will be equal to sigma x, and that will be compressive, so that will be m c by I minus m c pi by 4 c4, and that will be equal to minus m 4m divided by 4m divided by pi c cube. Now if I put the value minus 450, 4 times 450 divided by pi and c cube, 0.016 cube. So if we calculate it, so that will become minus 139.882 megapascal, or you can take approximately 140 megapascal. Okay, now the shearing stress tau, that will be xy, and that will be equal to Tc by j, or we can write Tc by pi by 2 C4, or we can write 2 times T divided by pi C cube. So putting the value, 2 T is 350 divided by pi C cube, 0.016 cube. So that will be equal to, the shearing stress will be equal to 54.39 megapascal. Now if I draw on this element, so we have normal stress sigma x, that will be minus 139.882 megapascal. We have a shear stress like this, because we are taking section over here, and due to shearing torsion, the shear stress direction will be like this. Okay, and that will be equal to tau xy is equal to 54.39 megapascal, and sigma y will be 0 because there is no stresses force in this direction. So now we find the state of stress at point H. Now let's calculate the max principal plane and the principal stresses. Okay, now let's see. So let's calculate part A, principal stresses. So let me draw the element over here again. So we have compressive stresses and we have shear stresses. So sigma x, tau xy. So sigma x was equal to roughly 139.882 megapascal, and tau xy was equal to 54.39 megapascal. Okay, so principal stresses and principal planes. Okay, let's calculate first principal stresses. Let's calculate sigma max, and minimum will be equal to sigma average plus minus radius, or sigma x plus sigma y divided by 2 plus minus under root sigma x minus sigma y divided by 2 square plus tau x y square. Now let's put the value. Sigma x is, sorry, this will be compressive, negative. So that will be minus 139.98 divided by 2 plus 0, because there is no sigma y is 0, plus minus under root minus 139.98 minus 0 divided by 2 whole square plus 54.39 square. Okay, now sorry, the shear stress will also negative because of the direction. Okay, and sigma z y is equal to 0. So since it's a square over here, so no need to write. So if we calculate the principal stresses, so sigma maximum is 18.67 megapascal, and sigma minimum will be minus 158.5 megapascal. Now if you look at the magnitude wise, the maximum stress is 158.5, but we are writing minimum because it has a negative sign. Okay, and now the principal planes, tan 2 theta p will be equal to 2 times tau xy divided by sigma x minus sigma y. That will be 2 times negative 54.39, again negative sign because of the direction. If this is the reverse direction for the shear stress, then we will take positive, divided by 139.88 minus 0. So this will give us the value of 0.7778 or 778, or 2 theta p will be equal to 37.88 degree, or theta p. So there will be two orthogonal angles. First will be 18.9 degree, and the second will be 108.9 degree. Means if I positive sign means I have to rotate counterclockwise direction. So if I rotate this in counterclockwise direction, and that will be from this, that will be theta p of 18.9 degree. So this is the principal planes, and we have a stresses, principal stresses on that plane, and that will be if I want to write, we have compressive stresses of minus 158.5 megapascal, and on this face we have a maximum tensile stresses, sorry, that will be minimum 18.67 megapascal. Okay, so that's how we calculate the maximum principles planes and stresses on the mechanical structure, that is in this case a axle of an automobile, for this problem. First we have to take a section, then you have to transfer force moment on that section, you have to find the stresses according to that, and then you can calculate the principal stresses and principal planes. And you have to consider that this method of superposition as well. If the stresses are produced with two load stresses are produced in the same direction, same nature, then they will add or subtract depending on the nature. Okay. Now, and the second part is we have to find maximum shearing stress of same point. So let's see how to calculate. Okay, now let's calculate maximum shearing stress at that same point. State of stress is given. We already calculated due to loading. Then we calculate principal stresses, maximum and minimum. So minimum minus over here minus 158.5 megapascal. Okay, now the maximum shear stress tau max is equal to the radius, or that was equal to sigma x minus sigma y divided by 2 square plus tau xy square under root. So when we put the value, so this will be minus 139.882 divided by 2 square plus minus 54.39 square under root. So when we put the value, so tau max is equal to radius, and that is equal to 88.6 megapascal. Okay. Now, if I draw a Mohr circle for this problem, or circle for this problem, graphically represent. So this is my sigma axis, this is my tau axis, and the sigma, the average stress will be equal to the average stress will be equal to 69.94, because sigma average is sigma x plus sigma y divided by 2. Sigma y divided by 2 is to put the values of sigma average, where we have a center of the circle, that will be equal to minus 69.94 megapascal. So this center will be at here, sigma average. So minimum will be sigma average plus radius, and that will be maximum, over here, sigma average plus radius, so that is 18.68, and minimum will be sigma average minus radius. And if you draw the circle, it will be something like this. And the maximum shear stress will be over here, tau max, and that will be equal to 88.6 megapascal. So this is, we will represent it graphically. Okay, let's see this problem. For the state of plane stress, determine a largest value of tau xy for the maximum in-place shearing stress is equal to or less than 12 psi. So state of stress is shown. So tau xy is unknown. So how much shear stress, loading shear stress we can apply, but we know that for that material, the allowable shearing stress must be equal to or less than 12 psi. And part B, we have to calculate the corresponding principal stresses. Now, if I want to write, so sigma x, I can write 10 ksi. Sigma y, sigma y is minus 8 ksi, and tau xy is unknown. Okay, and we also have given that the maximum allowable shearing stress, tau max, that is in plane is 12 ksi. Okay, now we know that tau max is equal to radius of that circle, Mohr circle that we discussed, and that is equal to sigma x minus sigma y divided by 2 whole square plus tau xy square. So that is tau xy is unknown and we have to find that one. Now, if you put the value, sigma x is unknown and tau max is 12 ksi, that we know. Sigma x is 10, sigma y is minus 8 divided by 2 square under root plus tau xy square. Now, if you solve it, so if you putting the value, so if you solve it, so tau xy is equal to under root 12 square minus 9 square, 18 divided by 2, 9, and that is equal to 7.94 ksi. So that the largest value of tau xy, it can be due to shear stress, transverse load, or it can be due to torsional moment, that can be 7.94 ksi on that uh, problem. Okay, now part B, we have to find the principal stresses. And we know that sigma maximum and minimum is equal to sigma average plus minus radius. Okay, sigma maximum and minimum, sigma average, sigma x plus sigma y divided by 2 plus minus under root sigma x minus sigma y divided by 2 whole square plus tau xy square. Now, in this case, if you put the value of tau xy, it will come back to 12 ksi, right? So that is equal to radius. This value was equal to radius. So it will simply, we can write sigma maximum and minimum, that will be equal to 10 minus 8 divided by 2 plus minus radius of, that will be 12. Or sigma max is simply 1 plus 12, that is 13 ksi, and sigma minimum will be 1 minus 12, and that will be 1 minus 12, that will be minus 11 ksi. Now, average stress is 1 ksi. Now, if I draw Mohr circle for that problem, so if I draw Mohr circle, so this is my sigma axis, tau axis. Now, maximum is sigma maximum, average stress, where we have center of the circle, and we have a sigma minimum. And if we draw Mohr circle, that will be something like this. Okay. And the maximum shear stress will be radius of the circle, tau max. Okay. Now, if I want to represent these stresses as shown over here, so we have calculated this tau xy, then let me change that. We calculated that was 7.94, that we calculated 7.94 ksi. Now, sigma x is 10 ksi, so let me put this is sigma x 10 ksi and 7.94, and this will be negative 8 ksi, and this will be minus 8 and 7.94. And if you draw a line, so this is representing our state of stresses given over there. These are my principal stresses, sigma maximum and sigma minimum are my principal stresses, and the maximum shear stress is tau max. And graphically we could present those stresses, and this is known as Mohr circle for plane stress. We don't use that much Mohr circle these days because of we have a lot of computational power, but if you want to find principal plane, we can find this angle, and in Mohr circle it will be 10 to theta p. And this angle, or this angle will be theta 2 times theta s. Okay. Now you can solve the problem as given in the assignment, and it will give clear the concept related to the principal stresses and shear stresses. So principal, what is the definition? Principal stresses again, at certain orientation where you have maximum and minimum normal stresses, and the shear stress will become zero. That is your maximum or minimum normal stresses, also known as principal stresses, and on which they are acting, those planes are known as principal plane. And at 45 degree to those plane, you will have maximum shear stresses with respect to principal planes. Okay, thank you very much, and we will see meet inshallah again.